I want to unpack a little bit of things we did in class today because we did it pretty fast, and with at least one section, we didn't actually get to the end. Let's think about this. So here is some group's data over here. They graphed the red line is the shoe dragged on the table. The blue line is the shoe dragged on paper. And we notice the red line is steeper than the blue line. Let's think about the y-intercept and the slope. Well, the y-intercept tells us the friction when Fn is 0, aka the shoe's not on the surface. And we expect the amount of friction when the shoe's not on the surface to be 0. And actually, if we look at it, it's pretty close. 0.2667 Newton, 0.4146 newtons. And we haven't really talked about margin of error in this lab, but it's pretty high. It's like a Newton. If you try to drag the shoe across the table, you might have noticed that the number kind of bounced around quite a bit. So like a y-intercept of 0.4 or 0.2 is really, really negligible. Also, like I said, the slope is steeper for the table and less steep for the paper. And if we imagine using an even rougher surface and do the exact same experiment, we would expect a steeper slope because all of these force values would be really high. So the slope would be kind of like this instead of like this or like this. So the slope tells us the roughness of the surface. Recall back to the spring lab. In the spring lab, the slope tells us the stiffness of the spring, and we called that the spring constant. So the stiffness was measured by the spring constant, and we used a symbol K. And we're going to do something very similar here. Here, we're going to call the roughness of the surface the coefficient of friction. That's the name we're going to give to the roughness of the surface. And the symbol we'll use for that is this Greek letter mu, or like I say, it's pronounced mu. It looks a little like an M, a little like a U. That's how you remember it. Don't write it like an M and don't write it like a U. Kind of write it like a script, like cool U, and you'll get pretty close. And now we can take y equals mx plus b, which we've used before, and we replace y, x, m, and b with symbols from the graph. And we're going to get ff equals mu times Fn. So Ff, remember, is the y-axis, is friction. Mu is the slope, so it's acting like m. Fn is the x-axis. And then b, like I said, was 0, so we don't write plus anything. Let's do a comparison now of these 3 labs we did. First, we measured force of gravity versus mass in the mass and force of gravity lab. And I said that the slope was g, the gravitational field. And that led to this equation we've been using a lot, Fg equals m times g. Then we did this spring lab, and we got a similar linear relationship. And the slope of that, I said, was called k, the spring constant. And that led to the equation Fs equals k times x. And today, we did the force of friction versus normal force lab, and the slope of that was called mu, the coefficient of friction, which gives us the equation Ff equals mu times Fn. And in your homework, you're going to see that just like we could use Fg equals m times g to solve problems, and Fs equals k times x to solve problems, we can use Ff equals mu times Fn to solve problems. All right, give your homework your best shot, and we'll go over it next class.